So we've taken a look at vector fields, we've also taken a look at electric fields, and we're able to come up with an equation for it. So now the question is, what happens if I want to calculate the electric field for distributed charges? What this distributed charge means is, what if I'm no longer looking at a point source for my electric field? What if I'm looking at an object? So our previous practice with our Mathematical Foundations chapter comes in very handy now, because there's different types of mass, as we know. We know there's linear mass, there's surface area, and there's also volume. So in terms of these different types of mass densities, we can also have different charge densities for different shapes and sizes of objects. So that means if I have a string that's charged, it means that I'm going to take a tiny snippet out of that string and call that dl. And that dl, the small tiny length that I have, is going to have a really small charge dq. And then I'm going to look at another point in space, point P for example, and try and figure out how much of an effect that little dq has at that point P. The only problem is I'm going to have to tally up all of the contributions from different dq's along the string at that point P. So as you can see, we can't do these calculations individually, especially as you chop up the string or whatever object you're looking at into smaller and smaller pieces. It just means more and more calculations. So that's where integration comes in very handy. You'll see that when we go through the exercises in this chapter, a lot of the math is pretty intensive, but that's why we have to show it to you. We're showing it to you to say that the math does get pretty intense, but there are ways in the future that we can try and minimize all of these efforts. So we're going to start from brute force math, and then later on we'll be able to streamline it quite a bit so that you can solve questions a lot faster. So in terms of looking at continuous charge distributions, which is the focus of this chapter, there are three different types of charge densities we have to know about. That means if we're looking at a string, we have linear charge density, because everything's just 1D almost. Then we have an object with a surface, and we have a surface charge density. After that, we have volume charge density, and that's represented by rho L, rho S, and rho V, respectively. In physics, we use different terms. For example, for linear charge density, we use lambda, but in this case, for ECE 106, we'll be using lambda for something else. So to make things simple, we're just going to use rho for all of the charge densities. So why don't we go ahead and go through the different charge densities, how we can calculate the total charge, and therefore be able to figure out how to solve different problems from that. So before we can even calculate electric fields, let's take a look at charge density. So what this means is we're going to be looking at charge distributions. So I'm just going to say before we looked at individual charges, and we now want to look at continuous charge distributions. So what does this even mean? It basically means, what if there were millions of particles with a charge on or in an object. So in other words, if I was trying to look at the effect of some charged object like this, which had tons of charges here, and it has a continuous charge distribution across the whole object, and I was trying to find its effect on a point P over here, then I'd have to consider the effect of this charge on P, this charge on P, and you'd have tons of contributions coming from different areas of the object. So in this scenario, it would almost be impossible to break this up into so many tiny pieces to be able to calculate the electric field at this point P. So to calculate dE over here, we'd have to do tons of calculations. So it's way easier to take a look at charge density and then be able to figure out the total charge of the object and how it would generate an electric field. So we can say we must introduce charge density so that we can calculate the total charge of an object or its electric field contributions. And so now we want to take a look at what kind of charge densities there can be. So let's ask ourselves, what types of charge density or charge densities are there? So before we answer that, let's think back. What other densities have we talked about? We've talked about mass densities. So remember, there's 1D, 2D, and 3D mass. With 1D, we have linear mass, and 2D, we have surface area, and with 3D, we have volume. So it makes sense that we have the exact same types of charge densities here. So we have linear, I'll just squish this over a bit so we have more room. We have linear charge density, which we'll call rho L. And keep in mind, rho L we're using in this class. In physics, we usually use lambda. The only reason for this is we'll be using lambda for something else later on in this course, so we don't want to get confused. So we have linear charge density. Next, we have surface charge density. Which we'll call rho S. And of course, we have volume charge density. Density. And this will be rho V. Okay, so we have our three different types of density, and now let's just go through this comparison chart to see what kind of differences there are. So in blue, I'm going to first draw the different types of shapes we could have. Let's draw this. It can be just a line that holds a charge. For the surface charge density, I'll draw some blob, and same over here, I'll draw the same or similar blob. And it's going to be 3D structures, one's surface, one's volume. So taking a look at the linear charge density to start, if I were to try and figure out the total charge of this entire string from start to finish, I'd have to cut it up into pieces, just like regular integration techniques. So why don't we cut this small piece out, and that means if there's a total length L, then this is going to be a change in length, which we'll call the differential length element. So we know that already. The one thing we're adding to this is there's a total charge Q associated with this and a total length L. So if there is a small baby length here, that means it's also going to have a small baby charge dq. So we call this the differential charge element dq. So then dq is simply going to be the density, or the charge density, times the mass element, similar to when we had the mass density. So we now have rho L dl. So if we wanted to calculate the total charge Q, Q would be equal to the integral of rho L dl. And if there was a uniform charge distribution, so if there is uniform charge distribution, where rho L is equal to rho naught, then Q would be equal to, you would take out the rho naught and get the integral of L dl. And in this case, you can actually simplify this, because the total length, when we integrate dl along the entirety of its length, we simply get L, the total length. So then you would have Q is equal to rho naught times L. Now, if the question said that the total length, that the total charge is distributed uniformly along the total length, then your rho naught could also be equal to a charge distributed over the total length, like this. If the question doesn't say that it's uniformly distributed, then your rho L might be dependent on some sort of function, which means your integration would become a little bit more involved. Okay, so on to surface charge density. With surface charge density, let's take a look at some piece that we can cut out from our shape here. So that's our surface, and from our previous experience, we know that this is ds. So that would be the differential surface area element. And the only difference here is that we're looking at a charged object, which means whatever tiny differential element we're looking at, in this case ds, it's going to hold a charge as well. And that charge is going to be dq. So now dq in 2D is going to be your surface charge density times ds. And if I wanted to calculate the total charge, it would be the integral, or the surface integral, of ps ds. And once again, if there is uniform charge distribution, where rho s is equal to rho naught, then my Q becomes rho naught, which I can take out, and I have the surface integral of ds. And this is basically my surface area S. So total surface area. So I can simplify this to rho naught S. The other thing is, if we're not given rho naught as a number, and we're told that there is a total charge and it's uniformly distributed over a total surface area, we can calculate rho naught by simply dividing the total charge by the total surface area. So hopefully you're seeing some connections between all of these because they're quite similar. And last but not least, we have to do another analysis for volume. So in this case, let's go with red, and we now have a 3D shape like that. And from our previous knowledge, we know this is dV, and we also know that because this object holds charge, or has charge, there's going to be a dq associated with a differential volume element. So this means dq is going to be equal to the volume charge density times dv, and q, the total charge, is equal to the integral of rho v dv. And once again, we take a look at what happens if there is uniform charge distribution. Now we have rho v being equal to rho naught. Then q is equal to rho naught times the integral of dv. But we all know that if we just integrate with respect to volume across the entire volume, it's just v, the total volume. So that means we can simplify this and write this as q equals rho naught v. And of course, if you're not given rho naught, but you're given the total charge and the total volume, then rho naught is simply equal to the total charge divided by the total volume. So just keep in mind, these are the different options you have when we're looking at different charge densities. You have linear charge density, surface charge density, and volume charge density.